Hi, I'm Marcus Kohler, a developer advocate here at PubNub. Today we're going to build out a dynamic matchmaking system designed for real-time multiplayer games. We'll show you how to use PubNub Illuminate, our matchmaking solution, and Epic Online Services matchmaking features to give you the option to create a dynamic matchmaking system. PubNub Illuminate brings the real-time intelligence to make matchmaking decisions on the fly, while Epic Online Services delivers battle-tested session infrastructure to reliably get players grouped, connected, and into a game at AAA scale. Now, if you've ever built or played an online game, you know how vital matchmaking is. Get it right means you've got a sticky competitive game loop that keeps players coming back. You may have heard of EOMM, Engagement Optimized Matchmaking. EOMM is all about using machine learning to predict how long a player will keep playing based on whether they win or lose a match. These systems are designed to maximize retention, but there are opportunities to build upon them to prioritize social connections and other ways players prefer to play. To optimize for social connections, we'll first need to understand player behavior. Illuminate injects player insights into the system and lets you process that data in real time, so you can update your matchmaking logic on the fly without pushing new code. You'll be able to track metrics like skill, latency, and player behavior to make smarter, more dynamic decisions. With PubNub Illuminate combined with Epic Online Services, you can get players into the game grouped up with friends and ultimately in an actual multiplayer match. But before we dive in, let's break down the core types of matchmaking systems that are commonly used today. First, we have skill-based matchmaking, or SBMM. This one matches players based on performance metrics like ELO or MMR. It's all about creating fair, competitive games. This can result in tight win/loss cycles and high-pressure lobbies, which can be great for some players, but not ideal for others. Next, we have region or latency-based matchmaking. Here, players are grouped based on physical proximity to reduce lag. This is super important for real-time gameplay, especially in shooters, fighters, or anything a little twitchy. And lastly, we have engagement optimized matchmaking, or EOMM. We talked about this earlier, but they're focused on maximizing player retention. Our goal here is to build a matchmaking system that considers the most important question when designing any experience, which is, who are my players and what do they enjoy? So here's what we're going to do in this series. First, we'll build the foundation of our system, a player queue, and a matchmaking engine based on a few predefined player metrics. Then we'll plug in PubNub Illuminate to start tracking real-time data. We'll offload decision-making to the edge so the logic updates live, no code redeploys needed. We'll iterate, refining the matchmaking process until it fits our players like a glove. Finally, we'll show you how to then take these well-matched players and send them into a match with Epic Online Services. We'll be able to test different strategies quickly, adjust variables on the fly, and even experiment with unique engagement models without breaking our game loop. So here's a quick overview of what we're going to be building. Feel free to pause and take a look at the tools and technologies we'll be using. And while we're here, let's take a closer look at this architecture. We're using PubNub for all the real-time messaging. That includes player queues, matchmaking decisions, and lobby notifications. Once two players are matched, we generate a lobby ID and send it to both the clients through PubNub instantly. Then we bring in Epic Online Services, and specifically sessions, to handle the multiplayer side, creating an actual game session, assigning players to it, and tracking the session lifecycle behind the scenes. All on infrastructure that's battle-tested to scale across millions of players. Epic Online Services gives us built-in session management, join tokens, and player tracking, so all we need to do is connect the dots. It can also serve as a fast way to get players into the game with their existing accounts, facilitate voice comms, and much more. Together, PubNub can work with Epic Online Services to create a smooth pipeline from being able to queue players, match players, and create a session. All built to handle high concurrency and real-time performance at scale. All right, that's the architecture. Now let's build it. If you don't want to build everything step by step with me, I've made the full project available on GitHub, so you can grab the code, set it up, and start experimenting right away. I'll drop the link in the description below. It's got all the pieces, the PubNub orchestration layer, the EOS session server, the quick setup instructions, and examples to get you matchmaking in minutes. So whether you want to customize it, extend it, or just use it as a starting point for your game, everything will be there and ready for you. Hey everyone, welcome back. So first we're going to make a TypeScript project for our server that is going to hold our matchmaking algorithm. So first we're going to cd into documents, and then I have a temp directory. I'm going to make a repo called real-time player matchmaking demo. I'm going to cd into that repo. Then we'll need to initialize npm. This will create our package.json to manage all of our dependencies. Now we will install the TypeScript tooling that we will need, plus the types for Node.js. TS Node allows you to run TypeScript files directly in Node without compiling first. TS Node Dev gives you hot reload, so your app restarts when you make changes. Types/node gives TypeScript access to all the built-in Node.js types like fs, path, and process. So these tools will just help us with working in TypeScript and make that a lot smoother. Next, the editor of choice I'm going to be using will be VS Code, but feel free to use any editor of your choice. I'm going to open up that repo that we have just created. Here I'm going to start off by making a main.typescript file. This will essentially be our entryway into running our server. So I am also going to rename where the package.json should look for the JS file. I'm going to compile this repository inside of a dist folder, so it is all compact when it is compiled. Here I'm just going to add some scripts inside of my package.json file to make it easier to compile from the terminal. So there will be a build script and a start script for npm that essentially is going to call that main.js file from that dist folder that I'm going to compile everything inside of. Next, we are going to install PubNub as a dependency, which will be our main library we will be using throughout this demo. We're going to be installing the core SDK for JavaScript. I will have to change my TS config to one I've previously created before. The root directory is where our source files live, and output directory is where the compiled files will go. In our case, /dist. Strict true gives us better type safety. ES modular interop makes it easier to import common packages like .env. The include section tells TypeScript which files to compile, and the exclude node modules and dist so we don't accidentally compile those. So that's a brief summary of what I pasted in the TS config. So next we will create a .env. This is going to hold our publish and subscribe keys from PubNub, which will allow us to publish message and subscribe to channels and receive messages. For this demo, we are going to be using PubNub to create a queue of players for our server. Next, we'll do npm i.env. This is because we're going to be using environment variables within our project. So now that we have set up our project, I just wanted to talk a little bit about the actual build layer of PubNub. I've covered a little bit of what PubNub Illuminate does and what we'll be using that for. Essentially, what we're going to be building with PubNub is that real-time layer. PubNub is the backbone of our real-time messaging. It's how players will send our matchmaking requests, match confirmations are delivered, and how we can push live updates like lobby IDs directly to players instantly. This will essentially allow players to be notified when a match has been created for them, allowing them to join that match from the session ID that we're going to implement later with EOS, and the publish key and subscribe key that we're going to go and get from the PubNub portal will be used for publishing messages and subscribing to incoming messages. Also, PubNub gives you a full-time toolkit for your game. You can use it for matchmaking, which we are in this case, or in-game chat, presence detections, friends lists, live leaderboards, whether that's knowing which friend is online, getting a notification that your score has been beaten on a leaderboard system, even spectator experiences, and it all runs on a reliable, scalable network across any platform or device. In this case, yes, we're using JavaScript to implement this server, but you could use PubNub in the front end on Unreal Engine, Unity. PubNub is completely platform agnostic, so it doesn't matter what language or framework that you are developing in, you will be able to implement PubNub. So before we start building anything, let's first set up our PubNub account and create a new key set. Head over to the admin.pubnub.com and log into your account. And if you don't have one, go ahead and sign up. It's entirely free to get started. Once you're in, you'll land on the apps and key sets page and go ahead and click the create new app button. I'm going to name my app demo. I'm going to select a region for my app context, which I'll talk about later, which just say the region closest to you. File sharing, we don't necessarily need. And then I'm going to enable 1 day of message persistence, which since we're just trying to make a queue, we will probably not need any message persistence either. I then got my publish and subscribe key, and here you can see my key setting. Here we are going to enable user metadata events, channel metadata events, and membership events. We will most likely not use membership events, but I'll talk about app context a little bit later in this video. But enabling these settings allows PubNub to automatically broadcast updates anytime a user's metadata changes, such as their skill level or region or latency or even match status. So first we're going to create our main class. Just going to be an async function, and make sure to call the main function as well. So that will just be our entry point. Next, I'm just going to create a source folder. Go on to create a core folder, which will hold our core logic for our matchmaking algorithm. We will create 2 files within this folder. One will be called the listener, which will listen to users joining the queue. And the next one will be called matcher, which will hold our matchmaking algorithm again and match players together based on different player metrics. Next, we are going to implement the listener class. First off, we need to import the PubNub SDK and .env so we can securely use our API keys from the environment variable file. This is a clean way to manage sensitive information without necessarily hard coding it or pushing that information to GitHub. Next, we will write .env.config, which loads our environment variables from our .env file. So in this case, our publish and subscribe keys will be available when we configure the PubNub instance. We will create the first class or function, start matchmaking loop, which will be an async function that essentially queues players that are looking to be matched together. We'll initialize our PubNub instance, passing in our publish key and subscribe key. Now we are going to subscribe to the matchmaking channel so we can listen for events in real time. This is where players will publish messages when they want to enter the queue. In this case, we will be using one channel, but you could see as a use case, you could split this up geographically to multiple different channels. So people publish messages to a certain channel depending on where they live. In this case, we're using demo matchmaking, but you can see in the future, you could use US East as a channel or US West as another one, and people could publish messages geographically depending on their geographical location. What this would do, this would essentially do latency-based matchmaking, which we went over at the start of this tutorial, which would minimize latency within your game. However, for this demo, we are only going to use one channel, and that is called demo matchmaking. Next, we are going to create a listener and listen for incoming messages on this channel. We try to extract the user ID and the message body. And for now, we will just log it to the console so we can inspect the event format. We will then later test this to see if it is all working after we have implemented this class using the PubNub debug console. Next, we will define an interval for how often we want to process that queue of players. This could be done via how many members are in the queue. In this case, we are going to just process a queue every 5 seconds, but we could make it in a way where we also process the queue based on how many people have sent in a message or have joined the queue. Next, we will just make a placeholder for where our process queue functionality will go, which we'll call our matcher.ts file. I'm going to go back to main and ensure that I am calling that start matchmaking loop function. And then we are going to build the project to make sure everything has built and run successfully. I forgot to insert a user ID into my PubNub instance, so I will go back and make sure that there is a user ID to identify this PubNub instance. I'm just going to call it server in this case. I'm going to rebuild my project and run it. Next, I am going to head over to the debug console to ensure everything works. As I can see, my server is currently running. The first thing I'm going to have to do is specify the channel ID that I want to create my test clients under. So the active channel that I will be using is called demo matchmaking, as that's the channel I want to send the messages through. I will create a client by clicking the create client button and send a message called here. We can see in the terminal that we have now successfully received that message and everything is working with our listener. So that person, Jack, in this case, has successfully joined the queue. All right, now let's talk about how we're going to process the matchmaking queue in real time using PubNub. At the top, we're going to have a simple in-memory queue that is just a JavaScript map that stores users who've joined the matchmaking system. Each entry in the queue contains a user ID and a basic message payload. We also will create a Boolean called isRunning. This makes sure we don't run the matchmaking logic more than once at a time. Now let's create the function that gets called every few seconds to process the queue. First, we check two things. One, is the queue already running? And two, do we have at least 2 users to match? If not, we just exit early. Because in this use case, it is a 1v1 example of a matchmaking system. If it was a 5v5 example, we would check if at least 10 players are in our queue. If both checks pass, we mark the system as running and log that the queue is being processed. Next, we will grab the users from the queue and extract their IDs. Now here's going to be the main logic. We are going to loop through each user in the queue, and we send them a PubNub message on their personal channel, which is just their user ID. So for this use case, or this demo I am creating, it is assuming that each user on the client side is subscribed to their own user ID to receive updates on their matchmaking progress. We will have to pass our PubNub instance down in order to send this message. However, each user will be aware that their matchmaking request is being processed currently. In the client side of the application or in the game, this could look like a loading screen or a time indicator to see how long they've been in a matchmaking queue for. And after we have notified each user that the process has begun, we can remove them from the queue using queue.delete. Finally, we will log the list of users we matched and whether the process succeeded or failed. We always reset the isRunning flag so the system is ready to go again. This is a simple but powerful tool that will let us simulate live matchmaking using just PubNub's core functionality. We'll improve this later by fetching user metadata and pairing based on real skill and latency data. But for now, this gives us a core foundation to work off of. We're just going to run npm build to ensure that everything has built correctly. And now we'll run npm run start. And now we'll go back to the PubNub debug console to test if our system is working. We are going to create 2 clients under the channel demo matchmaking and send a message through these 2 clients. We will create 1 client that is subscribed to the personal channel of the user ID, which will be Jack device. So in theory, if we send 2 messages in demo matchmaking, from two different users, we should receive a message on the user ID Jack device. So I'm sending my second message right now. And we have got clarification that both these users are in the processing queue. So now we know the system has worked. Next, we will implement our matcher file. We will first start by importing PubNub. This file will essentially match two users together based on metadata that later we are going to store in app context. We will start by making a simple function called process matchmaking. We will pass in the PubNub instance in order to notify our clients that a match has been created for them. And we will pass in the current members that are looking to be matched. I'm just going to create a placeholder here. Called pair users. I'll send in the member IDs that are looking to be matched together. Now, after my users have been paired together in pairs of two in this scenario, I will notify the players that a match has been created and a game lobby channel has been created for them. I will pass through my PubNub instance in order to notify the players and both the player IDs. I'm going to create a string that's going to represent the current game lobby channel. Later, we will be able to store metadata within this channel. For example, the type of match that they have joined. You can also use this channel to allow your players to communicate over in the form of a chat. We are going to notify our players now that a channel has been created for them by sending it to the channel of the player ID, which they should be subscribed to on the client side of their game. We will send the lobby channel within that message that has been created for those two players, so then they can both subscribe to that channel on their end. We will have to do the same for the second player as well. We will also send in the opponent that they will be facing in that message. They will be able to grab details about their opponent on the client side, displaying to your player who are they facing before the game actually starts. We will then publish a quick message to the game lobby channel just to verify that it has been created. I'm just going to change message to status, as that is the status of if the player has been matched or not. And for the first message, I'm just going to say starting game for player 1 ID versus player 2's ID. And I'm just going to console.log both their IDs. This is a placeholder of pair users. Later, we will bring in PubNub Illuminate to constantly update the algorithm and what it is doing based on live player metrics in real time. However, next, we are going to implement app context into our application. This will allow us to store different player metrics about our player. So whether that is their play style, their play frequency, what input device do they have, and we can update all these metrics and pull them in real time, allowing it for us to easily consider how we can match these players together. What I am using here is called BizOps Workspace. It allows me to visualize the objects that are stored inside of app context. In this example, I am storing completion rate, matches played, their platform, their play frequency, their play style, and all these things later will be pulled into the matchmaking algorithm in order to match these players together. I also store things like their skill level, etc. So next, we are going to create a new folder inside of our source. This folder is going to hold a script that is essentially going to simulate real players joining a matchmaking queue, while also updating and uploading their metadata like skill, region, playstyle, etc. to PubNub app context. Now, why is this important? This is important because your matchmaking logic relies on comparing users' metadata, like matching players with similar skill, region, latency. So we'll need to store this metadata in a PubNub app context so it can be retrieved and used during the matchmaking process. We will start by importing the PubNub and .env files. Next, we will initialize our PubNub instance with that server identity that we used prior by just specifying the user ID as server. We will be utilizing the same channel that our listener is subscribed to, called Demo Matchmaking, which we will publish our messages through in order to join players into a queue. Next, we will create some fake players. We will just name them player 1, 2, 3, and 4. Each player will include all fields that your matchmaking algorithm checks, like skill, region, latency, etc. We will then create a function called simulate player join. This function will create a temporary PubNub client as a player, publish a message to the demo matchmaking channel, and this will mimic the behavior of a real client or player joining a matchmaking queue. The next function will be set metadata and join. This function will iterate over each player, set their metadata using set UUID metadata, which you can find the documentation for in the PubNub docs. This stores their info in PubNub app context, so it can be fetched later. We will also call simulate player join to simulate joining the matchmaking queue from this function, as that is the function that publishes a message to that matchmaking channel. Next, we will just call set metadata and join function from the bottom of this file. So when this file is executed, it will immediately run that function. We'll be using an immediately invoked function expression, or a common async pattern in Node.js to do this. We will then go and modify our package.json so we can run this file easily. We'll be using the script that is set under set metadata. I will then build my project and start my server instance and run the set metadata class. As you can see, we've got confirmation that these players are joining the queue now. We will then navigate over back to BizOps workspace to see that the custom data fields that we set have been uploaded. We can see that their favorite weapon is a sniper, their input device is a controller, their latency is 42, the region's North America, and their skill is 85. So I'm going to slow down here a bit because I feel like this next part of this tutorial is very important, and it revolves around making that matchmaking algorithm that we're going to adjust with Illuminate in the future. I'm going to start by making a new file called constraints. These are going to be the constraints for our matchmaking algorithm. You can make these whatever constraints that you would like for your game and what makes sense for your logic. This is obviously just example constraints that I'll be using within this demo. So the constraints that I'll be using are max skill difference, max latency difference, require same region, I set that to true. We will require the same play style of our players, we'll set that to true. We'll try to block high toxicity players from being matched together. And we'll set the toxicity threshold to medium. This will all make sense when we actually go and start implementing the algorithm. However, these are going to be our conditions for our algorithm. So, in this example, you can't have a skill difference of 20, you can't have a latency difference of 50, etc. So now we're just going to make a quick function called getConstraints that are just going to return that constraints JSON. I'm going to go and import getConstraints from our constraints file. I'm going to set up two different type classes here. One will be player with metadata, which will hold an ID and the metadata of the player. I will go implement a player metadata type that we will need. I'm going to ensure that this player metadata type matches the metadata I am uploading to app context. So all the variables within this type will be the same as they were in our test file. So that includes skill, region, playstyle, latency, input device, toxicity, and favorite weapon. Input device in this case is either like a controller or a mouse, because in this example, my game is either on PC or on console. Now we're going to get into the real logic of this algorithm. We're going to implement this process matchmaking class. First, I'm just going to double check that the players being sent into process matchmaking are valid players, meaning they have the required metadata associated with them in order to be matched together, which includes that list above. I am going to pull in here the metadata for each player before I start the matchmaking process. To do that, I am going to send in that player ID, and I want to include the custom fields that we have uploaded to app context, so I will set that to true. So the metadata is stored in the results.data.custom fields because I've uploaded my own attributes into app context. The default fields of app context include UUID and name and email, but we want to store things like skill and latency, so those will be known as our custom fields. I'm going to go on and implement a function called isValidMetadata, just checking that they have those fields associated with them. This is going to return a player metadata type, which I have defined above, or a boolean if it is of type player metadata. Just going to ensure that meta is not null and that all those fields exist. I'm going to push the valid members into another list called valid members and push their associated ID and metadata. If they are not pushed into this list, I am just going to warn the console that I am skipping this user because he's not eligible for this matchmaking algorithm. This is just a safety check. However, I could default the custom fields to default values in a more of a production setting. I'm going to just ensure that there's no errors with this by running a catch statement. So later on when we test this, we could know if there's an error or not. Just going to output who the valid players are so I can ensure that this works. Now we are going to implement our custom matchmaking algorithm. We're going to call this pair users with constraints. This is your own custom logic. You do not have to follow the logic I am using to match these players together. And you can have your own custom constraints that make sense for your game. However, I'll show you a base type of algorithm that's just going to essentially match players together based on the constraints and the variables we have associated to those players as stored inside of app context. So this function is going to take a list of players, each with metadata like skill, latency, region, and playstyle. It loops through all the available players and tries to form the best matches it can while respecting our constraint settings. So that's the goal of this function. The function is going to return a tuple of player with metadata, so a list of 2. We're going to start by copying the list of players into an unmatched pool and prepare an empty pairs list to hold our successful matches. We will start by pulling in our matchmaking rules using getConstraints. These include things like max skill difference, max latency difference, whether players must be from the same region or similar playstyles. We're going to use a pretty greedy loop here. We are just going to grab the first player in the unmatched pool and compare them to everyone else still waiting to be matched. So for each comparison, we're going to calculate the difference in skill and latency and check if the 2 players are from the same region and have the same play style. We will also check the toxicity levels. If either player has a toxicity score above the allowed threshold, we skip that pairing, assuming that constraint is turned on, which later that will make sense when we implement PubNub Illuminate. But to do that, we're just going to convert the toxicity level from a string to an integer, or a number in this case. And that number will be either 1, 2, or 3, representing low, medium, or high. All these checks will then be combined into one condition called passes constraints. And if that condition is true, we will say this match is valid. As soon as we find a valid match, we store the index and break out of the loop. Again, this is a greedy approach. We don't try to find the best possible match yet. However, when we go and implement Illuminate, we will change this functionality in order to consider that. By the end of the loop, we're going to have a list of valid players that meet our current constraint settings. The setup will make it easy to debug and observe how players are being matched in real time, and we can adjust these constraints and immediately see different pairing outcomes, which makes it perfect for experimentation and optimizing matchmaking with Illuminate later. So after we have implemented our matchmaking algorithm, we are going to loop through our pairs of users because we have matched them together, but now our players have to know that they have been matched with another person. So we will have to notify them using PubNub that a match has been found for them. Later, we will call the EOS Sessions API to wrap a session around this match in order to store things like server metadata or game metadata that you might need to pull in for that player. When we notify our players, we will just publish 2 messages to them, as I said before, and we'll publish a message to that game lobby channel. I'm just going to console.log that game lobby channel to see what the ID is. I'm going to go back to my set metadata tests just to ensure that all of those metadata fields that I included in my algorithm are included in the metadata fields associated with app context. So I just have to modify my one function set UUID metadata and add their toxicity and their playstyle. So I'm ensuring that I'm uploading those data fields to app context. We will then have to open up our listener file and call the matchmaking function. I'm just going to pass down my PubNub instance so it can still publish messages and pass in my member objects, which represent the players within the queue. I'm going to go back to my PubNub listener that listens to the channel I'm subscribed to and make sure that the players that are publishing messages are added to that queue variable that I created earlier on in this tutorial. That way, when my interval runs to process the queue, I know those players are associated with it. So I'm going to do that by running queue.set. I'm then going to build and start my project, and I'm going to run that test class that I have created earlier. We can now see player 1, 2, 3, and 4 have joined the queue. The process queue is ran, and a game lobby has been created for player 1 and 3, as those are the players that were paired together. Player 2 and 4 did not meet my matchmaking constraints, so they did not get paired together. Now I'm just going to go into a little bit of why that is, just so you guys can visualize why player 3 and 4 were not matched, or why player 2 and 4 were not matched together, but player 1 and 3 was. You can see that up top, these are my matchmaking constraints that I have. And player 2 and 4 were not matched together because first they're from different regions and their skill gap and playstyle. The skill gap has too much of a difference and their playstyles are different than one another. Player 1 and 3 are from the same region. They have similar skill level, similar latency, and they have the same toxicity and playstyle. So they have met my matchmaking constraints and were matched together. Next, we will have to send this data to PubNub Illuminate. So we're just going to make a quick utils folder and a PubNub file. Our first function in this file is going to be update player metadata. This function will be initiated after that game is completed. So after both the players have completed their game, we're going to have to update their metadata within app context. This could be skill, this could be latency. You could really update whatever you prefer. I'm just going to make a general function here in order to do that. Before that though, I'm going to take the type classes out of Matcher and just put them into a types class and export them because I will need to use these types in multiple places in my repository. So what this update player metadata function will do is merge the existing metadata that we have within app context with any new updates that we have to push to these players. So after a game, their skill level could change, their playstyle could change, their favorite weapon could change. So I'm just going to merge this new metadata together. The next function I'll create inside of PubNub.ts will be sending PubNub data to Illuminate. For this, I'll just publish a PubNub message to a specific channel that I define. And later I'll be able to map that into a business object within Illuminate. I'll describe what that is later on in this video. But essentially all this function is going to do is publish a message to the channel Illuminate data with a custom payload that you define. This channel does not have to be Illuminate data. It could be any string that you would like to specify, as long as you map it correctly within Illuminate. We'll also be implementing this game.ts file. After the players are matched, we want to simulate a game. Obviously, this is just for the sake of this demo. In a real production setting, the game will actually be played out. But this function is going to take into account both the player's skill level, simulate a winner, and adjust their skill rating according to a certain factor or formula that you define. This function will utilize that update player metadata function that we defined inside of the folder utils. And it will also make use of sending data to Illuminate. We will define a session ID for this game that is currently running. We will also introduce a new variable from our constraints called the skill adjustment weight. This essentially defines how much their skill level should be adjusted after they win or lose a game. It is a multiplying factor from 0 to 1. Fast forward, what this function is doing is randomly selecting a player to win and updating their metadata with a new skill value and sending data to Illuminate, such as the session ID, both the player IDs, the skill gap that those players had, and the average skill of both of those players. Next, we will go back to the matcher file and just call simulate game after the two players have been notified that they have been matched together. We will pass in our PubNub instance and both of the player objects into this function. We'll then build the project and start it. And then we'll run that testing class that we had prior here. We can see that player 1, 2, 3, and 4 have joined the queue again. We can see a game lobby has created and the game has finished. Navigating back to BizOps workspace, we can check out the custom data fields and we can see that player 1 skill level is 43. What we originally started with inside of the testing class is 25, so we can see that their skill level has been updated accordingly after they have won that game. So the next part of this tutorial, we're just going to go into Illuminate. Illuminate is split up into 3 sections: business objects, dashboards, and decisions. So I'm just going to go into a little bit about what each one of these things actually means. So let's start with business objects. Business objects is essentially just how you get your data into Illuminate. You could think of them as containers for the data you want to use for decisioning and visualization inside of the PubNub platform. You define essentially 2 things within business objects. You define the data that you want to track. This can be what we're trying to track inside of Illuminate, like skill or latency or toxicity of my game. You can basically map any variable that you want inside of Illuminate using JSON paths. And if you're already using PubNub to map the data, then you just point Illuminate to the field that you wanted to use. And the second thing, you can aggregate that data by creating metrics like averages, counts, or ratios that let you track trends over time. For example, if I upload people's favorite weapon into Illuminate, I could count how many people love the new weapon that I just released into my game. Or if I'm uploading people's skill level, I can take an average of everyone's skill level within the game. So you don't just get to upload data, you actually get to aggregate that data. Dashboards allow you to visualize this data that is being captured in real time. And the next part of Illuminate is probably the thing I find like the most cool about this product is actually decisioning. So decisions allow you to automate logic that reacts to real-time events and changes in those business objects. For example, if the skill gap of everyone competing in your game is becoming too great, you can make a decision to try to prevent that, maybe activating a new algorithm or changing a constraint that will have a drastic effect on that algorithm. And this is all done in real time. There's no code redeploys or patches. And decisions, they're defined through rules. So they live right next to your data. So instead of building a complex backend with event processors and logic change, Illuminate does it for you in a serverless environment. And we will get into what exactly that means. So now let's go and start setting up our business object. So let's navigate to business objects inside of Illuminate. Let's give our business object a name and a description. Going to select the key set I have been using for this demo, or the application and key set I've been using for this demo. After that, we get to map data fields inside of our business object. These are editable at any time after the business object is created. So the first data field I'm going to map is the skill gap that we're sending to Illuminate. I'm going to select the category message and body, as that is where the data field exists. Looking back at our code, we can see this by looking at the message payload that we're sending into that Illuminate channel. And then the second thing I am going to map is the average skill within my game, which is also a number. And I'm just going to save that. So both of those data fields are now mapped within my game. I am now going to create a metric. Let's call it skill gap average. And this is essentially going to measure the average of the difference in skill within my game. It's going to process the data every 1 minute. And the second metric I'm going to create is taking the average of just skill in general within my game. Again, going to calculate that metric every 1 minute. I'm then going to navigate over to dashboards and create a player matching demo dashboard. I'm going to select my business object, which is player matching demo, and I have my two metrics there. I'm going to add those two charts and save it. I'm then going to navigate back to my repository just to see that it's all worked. So we just have to run that test class again. Now this time we run it, we should see in the dashboard that the metric or business object has been captured. And we can see that the skill gap in my game is 40 on average, and the average skill within my game is around 22. Now we want to create a decision based off of this business object. For example, looking back at my previous demo, we are tracking average wait time, and we have a max skill gap decision, which essentially allows people to pair together of higher skill difference. So if their skill difference, they could only pair together within a 20 parameter skill difference, now they can pair together over a 40 parameter skill difference, depending on how long my players are waiting inside of lobbies for. we're going to go and create a decision similar to that. I'm going to name the decision the skill gap decision, give it a description. I'm going to select the business object that it uses. You can either create a decision on an aggregation or an event. An aggregation meaning it is some sort of metric or threshold within your game that triggers the decision, and an event is some event in your game that triggers the decision. You can do either or. The aggregation is going to be based off of the skill gap average. When making a decision, you can either send a message, send a webhook, update a user's metadata, update a channel's metadata, or update a membership's metadata. For our setup, what makes sense right now is either updating a user's metadata to change some parameter within a user, or sending a message. I'm selecting sending a message because that constraints file that we created prior, I want to modify that so the constraints are now dynamic. I will then go and select my key set that I wanted to use to send this message, which will just be the same key set that I've been using all along. I'm going to send it across the channel conditions. I am going to put a variable into my decision or my action in this case. The variable is going to be called average skill gap. You can do this by using the $ curly braces syntax that you see up above here. This will allow me to adjust a variable depending on what threshold has been met within my aggregation. Now I get to name my variable, so I'm just going to name it skill condition. My action name is going to be the adjust skill condition action, because we're going to be adjusting the skill condition constraint within our project. Now we're able to add rules. So if the average skill gap is greater than 50, we're going to set the skill condition to 30. If it's less than or equal to 50, we're going to set the skill condition to 50, making that constraint that we had earlier more dynamic within our code base. We're going to activate this decision now. We'll have to go back because that was not a valid JSON within my action. So just ensure that that's a valid JSON. I just had an extra curly brace. Save that. Now I'm just going to navigate back to the player matching demo dashboard. I just want to edit it so I can attach my decision to the business object that I'm currently visualizing. To do this, I'm just going to click edit on my dashboard, manage, and attach the decision that I just created, which is the skill gap decision. And then I'm just going to click save. Obviously no threshold has been met yet, but this is where you'll see the actions firing off. So now we're actually able to go back to that constraints file that we had prior, and we're able to attach that max skill difference constraint directly to Illuminate. We're going to start off by initializing a PubNub instance, as we always do. In this scenario, I'm just going to make the user ID Illuminate Sim. Just something descriptive to say that this is another user listening for constraint changes. Then I'm just going to make a generic function called update constraints, which will just be a safe wrapper to merge in new values without overwriting the entire object. We'll then subscribe to the channel called conditions. This is where we expect the live config updates to be published from Illuminate, as we set that up through our Illuminate action. So essentially we are going to check for incoming messages that contains keys that we care about, like max skill gap. If it does, we map that to our internal config using update constraints and log the results so we can see what's updated in real time. If someone were to publish an invalid message from Illuminate, it would just throw a warning instead of crashing or silently failing, which will be super helpful for debugging. So why does this matter? I think this is a great example of just real-time infrastructure done right. We're not hard coding configs, not relying on stale caches, and not burning cycles redeploying configs. With PubNub, we're listening to our channel, and the moment a constraint changes, our system adapts in real time. It's simple, scalable, and super powerful when paired with PubNub Illuminate or live matchmaking. So I've added some more players inside of my simulation that I'm running here. Just to get that action to fire off, I'm just going to build my project and start it. As you can see, we've been subscribed to the conditions channel. And our 9 players have joined the queue. The 9 players have been matched together now. And our constraints have been updated. So that means that Illuminate is working. The skill difference of these players passed the threshold of 50, which was in the rules that we set. Now we can go and visualize this action firing off by navigating back to the dashboard. We can see that there's an action that's fired off there. Because the skill gap average went above 50, those actions are fired off, and trying to reset that skill condition, which was called max skill gap, back down to 30, so that does not happen anymore. Now that we have finished integrating PubNub Illuminate and can track real-time insights like match fairness, latency, and player behavior, it's time to shift gears and bring in multiplayer infrastructure. In this phase, we're setting up Epic Online Services, or EOS, to handle session management. EOS gives us a powerful way to create, manage, and track multiplayer sessions, including player joins, lobby visibility, and server coordination. So while Illuminate helps us make smarter decisions and smarter matches, EOS ensures we can host and manage those matches at scale. Let's dive into how to get EOS running locally and tie it into our matchmaking flow. First, we will have to go and create a product. I'm going to call that product Player Matching Demo. Next, I will have to navigate to product settings and add a new client. I'm going to name this client Player Matching Demo Server, as this will essentially authenticate my server so it is able to create a session within EOS. I'll need to create a policy for this client, so what it has permission to, and I'll select the policy type as a trusted server. A trusted server in EOS is a backend component that securely performs privilege operations on behalf of your game, like creating sessions, validating join requests, or managing player state. It's trusted because it uses your client ID and client secret to authenticate directly with EOS, and it is not exposed to the public of players. Next, after we have created our client, we're going to go and install the EOS SDK. We're going to be coding the server side of this in C++, so we will install the C Core SDK for EOS. After we have installed the SDK, we can now go and unzip this file. And this is going to give us access to all of that API functionality for creating, starting, and destroying sessions within EOS. Now that we have our project set up on EOS, we're going to go in and start coding our EOS integration. First, we will start by making an EOS folder. Next, we will navigate into this folder and make a .env. I'll paste the example.env that I had on my previous project, but in the future, we'll need to get our product, sandbox, deployment, client IDs, and our client secret. We'll also specify a server port inside of this .env to specify what port the server is going to be running on. Next, I will go and make an EOS API file. At the top of the file, we will include our core headers, so standard C++ headers like iOS stream, future, and vector. We're going to include boost.json for parsing and serializing request data, the Crow web framework, which gives us lightweight routing and HTTP support, and of course, all the necessary EOS SDK headers for sessions, auth, logging, and core platform access. We will add a if statement for Apple or Mac OS. So we can run the EOS event loop through CF run loop run in mode. This I'll touch on a bit later, but it is essentially for threading the tick of the EOS platform, because we will constantly have to run a tick so it can process our requests. And next we will define our global EOS handles. These are core to how EOS works. So the platform handle is the base of the entire EOS SDK. Everything flows through it. The session handle is how we're going to interact with multiplayer sessions. And global session search handle is reserved for future matchmaking search operations. So the next part is EOS requires regular ticking to process interval events. So we need to define a function called tick EOS that runs in a loop and calls EOS platform tick every millisecond. This ensures things like session updates and async callbacks continue firing, even in a headless server. So while making this function, first we have to ensure that the platform handle exists. As said before, everything flows through the platform handle. And then we will call EOS platform tick, which is the API that ticks EOS. And every 300 ticks, I am just going to output that we are ticking the EOS platform. And this can be used for testing later on. Now we get into the real heart of the integration, which will be our initialize EOS function. So here's what's going to happen. First, we will initialize the core SDK with a product name and version. Then we define platform options. This is where we inject all of our credentials using environment variables. That includes the EOS product ID, the sandbox ID, the deployment ID, the client ID, and the client secret. We make sure to run in server mode by setting B as server to EOS true. Then we will create the platform handle and grab this sessions interface. If any of this fails, we will just print a clear error or exit early, which will be key for debugging later on. Next up is create session. The create session function takes in a unique session name, usually something like the match and then the ID of player 1 and player 2. We will first check if the session handle exists, as we will need that to create our session. Next, we will have to create session modification options. These are just essentially our variables that we will be using within our session. Next, we will set the bucket ID inside of these options. The bucket ID can be whatever you prefer, but the sessions that we create will be grouped under this bucket ID, so they are easier to find within the EOS dev portal. The next thing we'll do is set max players to 2, as this is a 1v1 matchmaking use case. So the max amount of players that can belong within a session are going to be 2, or a match in this case. Next, we will send those options or those settings for our session to EOS by calling EOS session create session modification. We'll see if the result is a success. Next, we'll set our bucket options or settings just to the latest API version, and we will just call it default bucket. This will essentially create our bucket for us within EOS. And lastly, we will call EOS sessions update session to finalize the creation of this session, passing in our session handle, our update options, and a callback which we will implement after this function. With this EOS sessions complete callback, we are just going to ensure that the session was created successfully and that EOS got our request. So we'll just have a bunch of output statements to ensure that the session exists. Next, we will create our first HTTP endpoint. The first one will be a post request for matching players. This will take in 2 player IDs, build a session name, and call create session. If the session is created successfully, it will return a JSON with the session ID. This is how you would hook up your matchmaking system or front end to trigger new sessions in real time. And we will format a JSON for the response. We will also define another function called destroy session. So when the game is done, we will then be able to take down the session that the players are using to run their game. This will take in a session ID and the callback logs, success or failure, and the route will just respond with a JSON message confirming the result. We will destroy the session by calling EOS sessions destroy session and just log the response. We'll also just have to define a destroy session callback just to ensure that the session has been destroyed successfully. In the same way, we are going to implement a start session. This will take in a session handle and a session name or ID. So this API for a start session is typically what you would trigger right before players are ready to connect to a live game session. And just like the other flows, we will register a callback for handling errors like session not found, invalid parameters, or sync issues. And we will start the session by calling EOS sessions start session, passing in our session options and our session handle. Now the main is going to be the core of this functionality. So first we will have to call that function initialize EOS. Obviously this will initialize our session handle and our platform handle, allowing us to create sessions and tick the EOS platform. Next, we will start the Crow HTTP server in a background thread on a port defined by the server port inside of your environment variables. For mine, I'm going to set it to 8080, and I'll get to that in a little bit. And finally, I'm just going to start an EOS tick loop. I'm going to make routes to those functions that I created. So the matchmaking function, which essentially creates a session for 2 players, a start session route, and a destroy session route, which is essentially just going to call those functions and format a JSON in response to see if they were a success or failure. And finally, I'm just going to start the EOS tick loop. On macOS, we use cfrun loop run in mode to process the tick. On other systems, we would just sleep every 100 milliseconds and tick manually. But since on Mac it blocks doing that, this cfrun loop run in mode is just a workaround for running a thread within a C++ environment. Now I'm just going to go back to the EOS dev portal. Here I'll just be able to grab those environment variables that I specified before. So that includes the deployment ID, the sandbox ID, the client ID, and the secret key. And I will be able to input those into my .env. Next, I can export that env using the following commands. So when I run this project, I have that .env loaded into my C++ project. And next, we will build the project with this command. This command wires everything together: the EOS SDK, Boost libraries, Crow Web Framework, and system frameworks like Core Foundation. And next, we can just run the project after we build it by using /EOS_API. I'll make sure to link the build command within the README of this project as well, so you guys don't have to worry too much about memorizing what this whole command does. After we have built the project, we can see that the EOS SDK has been initialized, the platform handle has been created, and the session handle has been created. The server is running. So now that we can see the server is running on a local host, we can go and now implement a create session API within our root project that we initially used to integrate PubNub and PubNub Illuminate. We will just be calling that localhost /matchmaking request and passing in a JSON containing the player 1 and player 2 ID and logging the response from that request. Similarly, we'll be creating a start session API that will communicate with our C++ server, passing in a session ID as a string and returning a promise as a Boolean, either true or false, whether the session was created or not created. And lastly, we'll create a delete session API within our project, passing in a session ID, specifying which session to delete, and just logging the response to see if that's successful or not successful. Next, we will go back to our matcher file. We will need to modify this to create sessions, start sessions, and delete sessions. So first we'll have to do some refactoring. We'll go into our game file, and instead of specifying a session ID inside a simulate game, I'm just going to pass one in. I'll copy the string that I was using previously and go and delete that session ID. Now we'll have to go and refactor our matcher class, passing in that session ID. After I've specified the session ID, I will go before I notify my players and create a session so they can play out their game within an EOS session after they have been matched together based on their playstyle, toxicity, skill level, whatever player metric you used within Illuminate. After I have notified my players, I will go and start that session because they are ready to play their game. And as I said before, you should always start a session when the players are ready to play that session out or play that game. And then after the game has been completed, I will go and delete that session using our delete session API. So the process here is I will go and create a session first. I will notify my players that that session has been created. I will then start that session. I will run the game. And then after the game has been finished, I will now go and delete that session within EOS. Now going back and testing my logic, I first have to build my repository. After I've built it, I'm able to start the repo again, run my test logic. I can see that my server is running on the left-hand side. These players are being processed within a queue. They are now matched together. Now I can see that a session has been successfully created for player 3 and player 8. And since the game is done, this session has also been successfully destroyed for those players. Now I created some sessions that I didn't delete inside of the EOS dev portal so I could show you guys where this would exist if you want to visualize these sessions being played out, or even if you wanted to visualize what metadata you are storing within these sessions, such as invites, the IP address of the session, any session metadata that you might want to store about the game, such as the game mode that they are playing. To do this, we are going to go and navigate to Matchmaking, and we're going to search by buckets. We called our bucket the default bucket, and after we search what the default bucket is, we see 4 sessions inside of there, and we can see that our sessions are being created successfully from our server. And that is it. You now have the full functionality of a real-time matchmaking system powered by PubNub and Epic Online Services. What we built so far is player state tracking, real-time matchmaking triggers with Illuminate, secure session management with EOS, and live analytics to make it all smarter over time. If you want to dive deeper or expand this into your game, everything is up on GitHub with the link in the description. Feel free to fork it, play with it, or integrate it into your own project. If you've learned something today, drop a like, maybe subscribe, and let me know what you'd build with this kind of setup.